Hey guys, so the last couple days we've been talking about physical properties. We started by going over some qualitative physical properties, then we looked at some quantitative physical properties, focusing mainly on the characteristic type of quantitative physical properties. Today we're going to be talking about some chemical properties briefly, and then we're also going to be talking about chemical change. Now, a few lessons ago when we were doing the physical properties lesson, we went over at the end some examples of different types of change, and I asked you to identify if they were physical or chemical. Today, it's going to become even more obvious how to differentiate between those two as we look specifically at what chemical changes entail. Okay, so this lesson is chemical properties. Essentially, you need to be able to use this information to identify the evidence of a chemical change and then apply that to differentiate between physical and chemical changes. A chemical property is any property of a substance that describes its ability to undergo chemical change or a change to its composition. When this happens, anytime you have a chemical change or a change to a chemical's composition, what that means is you're making at least one new substance from the original substance. And this will happen anytime there is a chemical reaction. All substances have chemical properties. Even if you don't think of a substance as being a chemical or being reactive, all substances have chemical properties. The air around us has chemical properties. Water has chemical properties. Anything in your fridge has chemical properties. My pen has chemical properties. Everything has chemical properties. And we use a lot of these chemical properties in our everyday life. When we are baking, we're taking advantage of chemical properties. When we're cleaning, when we are combusting or burning things, all of that is taking advantage of that substance's chemical properties. A chemical change is anytime we change an original substance to something new, and that could be one new substance or multiple new substances. Essentially, all we're doing is we're taking our substance and we are rearranging the atoms into a new substance. All of the atoms are still there, all of the components of that original substance are still there. We have just rearranged them differently. This is important because the law of conservation of matter says that matter is never created or destroyed. It is just rearranged in chemical reactions. So you have to have the same number of particles in your reactant and in your products. They're just going to be arranged differently. So if we look at this example at the bottom here, if you count all the red circles that you start off with, you'll have the same number of red circles in your products, and same with the white and black circles. Okay, so when you're looking for evidence that a chemical change has occurred, there are 6 pieces of evidence that we will be looking for. If a color change happened, if the odor changed, so it smells different, if bubbles have formed and not from heat, if a precipitate forms, which is a new solid, or if there was a change in temperature, and the last one, any production of light. Now, it is important to note that when we are looking for these pieces of evidence, they have to be things that happen on their own during the course of the reaction, not something that you're causing. So for instance, you might be able to change the color of something by adding food coloring or by drawing on it with a marker. That doesn't count as a color change. A color change is like if I take 2 clear solutions and I mix them together and I get a blue solution. The color is coming from something that I haven't added. But if I take a clear solution and I add a blue solution and it turns the original solution blue, that's not a color change. I've caused that to turn blue by adding something blue to it. Same with bubbles. I mean, if I put something on a hot stove and I start seeing bubbles, that doesn't describe bubbles that have formed on their own. They're forming because I have heated the solution up. Same with a change in temperature. A change in temperature can't come because I'm heating something in the oven, or I put it in the freezer, or I took it out of the freezer. Those are just like naturally freezing or melting on their own because I have removed them from a cool environment or put them into a hot environment or whatever. With a change in temperature would be, again, I take two room temperature solutions, mix them together, and now I have a really hot solution or a really cold solution. It's happening on its own. Okay, so a color change, again, is just you have a substance that is going to be changing colors on its own. An odor change, so it's producing a smell on its own. That could be a good smell or a bad smell. So the example here is some rotten fruit. So the smell of like food that is rotten is an odor change. That is a chemical change that has happened. Bubbles forming, that actually tells us that one of the new substances that is being produced is a gas. So for example, if you put lithium, which is a metal, into water, it produces hydrogen gas, and we see that in the form of bubbles. Same is true for if you put like sodium or potassium in water as well. A precipitate form, which is a new solid product that forms when you mix two non-solids, usually liquids, together. It could be kind of powdery, and sometimes it will just seem like your solution has gone foggy, but if you let it sit for a while, the powder will actually settle at the bottom and you can see that you have a new precipitate. So that's what this is showing kind of at the bottom of this test tube here, is a precipitate that has formed. Temperature change, that could be it either getting colder, which means that energy was absorbed by the reaction, or it's getting warmer, which is a sign that energy has been released from the reaction. So either endothermic or exothermic reactions that are happening. And then the last one, light, you might see this as a spark or a fire as opposed to just like a lasting glow. But that would also happen if you have, say, potassium in water. We already talked about the fact that potassium in water releases hydrogen gas, which is highly flammable. Potassium in water also releases a lot of heat energy, and that heat can ignite the hydrogen gas, which we see as fire. So yeah, if you see any of those 6 pieces of evidence happening, again, on their own, that is a sign that a chemical change has happened. If you don't see any of them, then it's probably a physical change. Physical changes can also be reversible, but they're not always reversible, and also some chemical processes are reversible. So that's not a great way of identifying whether or not something is a physical or chemical change. So you might have done that in previous grades. Instead, we like to use those 6 pieces of evidence. Chemical changes are then used to identify what the chemical properties of a substance are. So for instance, if something produces fire, the chemical property might be that it's flammable. If something changes color, like if a metal changes color from like a silvery color to a rust color, that tells us that it oxidizes easily, or it reacts with oxygen to produce a rust of some sort. If you have something that is supporting other flames to be burnt when it's reacted with, that means it's an oxidizer. So for example, I might take some methane, which is a gas, put it with some hydrogen peroxide, and I can burn the methane. So that tells me, 1, that methane is flammable, but 2, that hydrogen peroxide is an oxidizing agent. So that's one of its chemical properties. So there's lots of different stuff like that. You might just be able to tell that it's really reactive or that it's unreactive. All of those are chemical properties. We can then use chemical properties to identify a substance. So substances that look really similar and are hard to identify or distinguish between them based on physical properties alone, we can differentiate between them using chemical properties. So how do they react with other substances? So yeah, chemical properties can actually be more useful than physical properties in terms of identifying compounds. Okay, so what I would like you guys to take some time to do is go through all of these examples here and write in your note whether they represent a physical change or a chemical change, and which piece of evidence you've used to identify any chemical changes. And then, so pause the video right now and do that, and then I will take it up. I'll just go through them really quickly. Okay, so frying an egg, that is a chemical change. We know that because it goes through a color change. For instance, the whites go from clear to like a solid white. Toast, if you toast bread to make toast, that is also a chemical change because the toast changes color. There's also a smell associated with it. Cracking eggs, that is a physical change. You have broken the shell, but nothing about the color or the smell or anything like that of the shell has changed. Boiling water, that is also a physical change. We talked the other day about how anytime you have a change of state, that is a physical change. And even though there will be bubbles in boiling water, they are there because of heat that you have applied. Fresh lemonade, that is also a physical change. Because you're either just mixing like a powder with some water, in which case that is dissolving, and dissolving is always a physical change. Or maybe you just like squeeze some lemons in. Again, you're just mixing compounds, but they're not reacting with one another. And any change of color that you see to the water, maybe it goes from like clear to yellow, that's because you have added something yellow to it. Baking a cake, that will be a chemical change. You'll have a change in color and a change in smell associated with that. Slicing bread, that is just a physical change. You're just cutting it, you're not reacting it in any way. Lighting a match, that is a chemical reaction that is happening there. If you've ever like lit a match, you can like smell the like kind of sulfury smell that comes with that, or whatever smell that is. Roasting marshmallows, again, there's a color change there, so that's chemical. Mowing the lawn, you could kind of go two different ways with this. I'm going to say it's more so physical because you're just cutting the grass. Now, there is a scent associated with that, but that's because grass is a living thing and it actually releases chemicals when it's injured, and that's what we're smelling. It's not a reaction that's taking place in the process of cutting. It's like a release of chemicals inside the grass. But there won't be one that complicated on a quiz or test. Fireworks, you've got the change in color, that is chemical. Digesting food is chemical. I mean, you can't really tell what necessarily is happening in your stomach, but you might know that the food reacts with like hydrochloric acid and stuff like that to be both chemically and physically broken down. Rusting nails, you'll have a color change, so that's a chemical change. Melting ice, that's a change of state, so it's physical. And breaking glass, also physical. You're just changing the shape, it's still glass, it's just tinier pieces of glass. Okay, so that's it. Let me know if you have any questions about that.